A gearbox is overheating at altitude, and the two men flying have about 90 seconds to decide whether to trust the machine or fight it. The temperature gauge on the right prop rotor gearbox is climbing past its limit. Procedure says convert to airplane
Engaging
mode,
automated
level
corrective
off,
controls.
get the engine load down before something inside that gearbox seizes. The pilots start the conversion. The nacelles rotate, and at 86 degrees of nacelle tilt, almost fully forward, almost out of the danger zone, the clutch inside that gearbox locks up anyway. Both engines are suddenly fighting the same shaft at the same time. There is no time left to unwind it. The aircraft is a V-22 Osprey, and in the next few seconds, the exact mechanical compromise engineers built into this airframe 40 years earlier is about to decide whether 5 people survive the flight. That compromise has a name. It is called cross-shafting, and is the reason the V-22 can lose an entire engine mid-flight and keep both rotors turning. It is also, under the wrong combination of heat, torque, and timing, the reason a single point of failure could take down the whole aircraft at once. To understand why the Marine Corps accepted that trade, you have to go back to a problem nobody in 1980 could solve with a helicopter or an airplane, because neither one was built to do what the mission demanded. 8 helicopters fly into the Iranian desert to rescue 52 hostages held in Tehran. 3 fail before the operation even begins. Sandstorm damage, mechanical faults, 1 aircraft simply unable to continue. A refueling aircraft and a helicopter collide in the dust at the staging site. 8 servicemen die. The mission is aborted before a single hostage is freed. Operation Eagle Claw becomes the case study that defines the next 20 years of American vertical lift design, and the conclusion the Pentagon draws from it is brutal in its simplicity. Helicopters are too slow and too short range to survive a deep strike rescue. Airplanes are fast and long-ranged, but they need a runway that doesn't exist in hostile territory. Nobody wants to compromise between the two. They want an aircraft that refuses to choose. The concept already has a name and a scarred history. Tilt the rotor axis itself, and an aircraft can lift like a helicopter and cruise like an airplane. Bell Helicopter tested it once before in the 1950s with a prototype called the 15-3. It flew. It also very nearly killed its test pilots because nobody yet understood a phenomenon buried in the physics of a rotor mounted on a wingtip, whirling flutter. Push a rotor system to a certain speed on a sufficiently flexible mount, and the blades stop behaving like a stable disc. They start whipping in a widening, self-reinforcing spiral, feeding energy into the wing itself with every rotation, until the wing starts oscillating in sync with the blades. The 15-3 came apart in the air during testing because engineers underestimated exactly this coupling between rotor and structure. Rebuilt, redesigned, flown again for another decade of data collection, but the lesson stuck. Any tiltrotor built after the 15-3 has to treat whirling flutter as a design constraint, not an afterthought. Ignore it, and the aircraft tears itself apart from the wingtip's input. Bell carries that lesson into the next test bed. The 15-15, first flown in 1977, smaller, twin turboprop, built specifically to prove the whirling flutter problem could be engineered around rather than simply avoided. It works, and on the strength of that data, the Pentagon commits to something far larger, a joint service program forcing the Marine Corps, Navy, Air Force, and Army to share one airframe, one rotor system for different missions. The JVX program becomes the V-22 Osprey, and its central engineering fight is no longer can a rotor tilt. It's can a rotor this large, mounted this far from the fuselage, survive its own aerodynamics without flying apart. Here's the mechanical contradiction sitting underneath everything else. A helicopter rotor is enormous and slow-turning because it needs a huge disk area to generate lift at 0 forward airspeed. An airplane propeller is small and fast-turning, optimized purely for forward thrust. Those are not two versions of the same design problem. They are opposite problems, solved with opposite geometry. The V-22's answer is a 38-foot rotor. helicopter scale for hover lift, bolted to a nacelle that physically rotates the entire engine and transmission assembly 90 degrees between hover and cruise. Everything downstream of that single decision. The gearbox, the driveshaft, the actuator that performs the tilt itself, has to survive a structural environment no prior aircraft component was ever asked to survive. Start with the actuator because it's the single mechanism responsible for the whole transformation, and it has to fight physics that reverse direction mid-flight. In hover, the actuator is holding the nacelle against gravity and rotor thrust pulling it one way. In cruise, aerodynamic loads flip that relationship, pulling the nacelle the opposite way. The actuator isn't holding a static position under one kind of load. It's cycling between compression and tension thousands of times over an aircraft service life on a mechanism bolted to the single most structurally stressed point on the entire airframe. The wingtip where every gust, every maneuver, every rotor vibration concentrates its energy. Engineers rejected a conventional gear-driven actuator early because a single gear train under that kind of reversing load has exactly one failure mode. Jam it once, hard, and the nacelle is frozen wherever it stopped. Frozen at 90 degrees on approach to a ship deck is a helicopter landing. Frozen at 90 degrees at cruise speed is not survivable. The solution engineers settled on is a double telescoping screw drive, two screw-driven actuator sections nested inside each other, sharing the load across two separate mechanical paths instead of one. Split the load across two screws, and a partial jam in one path doesn't freeze the nacelle. The second path keeps driving. Its redundancy built directly into the geometry of the actuator itself, not bolted on as a backup system elsewhere in the aircraft. Lose half the mechanism, and the nacelle still moves. That single design decision, spread the catastrophic failure mode across two independent load paths instead of eliminating it outright, becomes the template for almost every critical system on the aircraft. Because the actuator isn't the only place the Osprey concentrates irreducible risk into a single component. The drivetrain does it too, and at a much larger scale. Here's the deal the V-22 makes with itself. The two engines aren't independent. A drive shaft runs the entire length of the wing, mechanically linking both prop rotor gearboxes, so that if one engine fails completely, the surviving engine can drive both rotors through that shaft. Lose an engine at 300 feet with a full load, and the aircraft doesn't fall out of the sky. It keeps both rotors turning on half the horsepower it had a second earlier. That's the safety case. It is also, mechanically, an enormous bet, because now the single most catastrophic failure mode on the aircraft isn't losing an engine. It's losing the shaft that connects them. And that shaft doesn't get to sit still. The wing itself is flexing constantly, under gust load, under maneuvering load, under the sheer vibration of two 38-foot rotors spinning at the wingtips. The nacelles are rotating through the entire conversion sequence. The drive shaft has to keep transmitting full torque at full RPM, while the two ends of that shaft are physically moving out of alignment with each other in real time. A rigid coupling would tear itself apart in the first few degrees of misalignment. Engineers needed something that could flex constantly, transmit enormous torque, survive tens of thousands of flight hours, and do it without ever being lubricated in the field, because a wing is not a place you want routine maintenance crews servicing a coupling mid-deployment. The component that solves this is almost absurdly elegant for something buried inside a wing. A multi-disc convoluted diaphragm, flexible coupling. Picture a stack of thin, precisely contoured metal discs, bolted alternately to each end of the shaft, each disc slightly convoluted, corrugated, not flat, so the stack can flex like an accordion while still transmitting rotational torque cleanly through the metal itself. No gear teeth, no sliding contact surfaces, no lubricant to break down, leak, or contaminate. The torque path runs entirely through the elastic bending of the discs. That coupling keeps the shaft spinning at roughly 6,300 revolutions per minute, while tolerating misalignment of up to 3.5 degrees between the two ends. A tolerance that sounds trivial until you remember this shaft, is running through a wing that's actively bending under load, and a nacelle that's mid-rotation through its own 90-degree tilt sequence. This is the exact system that failed in the incident that opened the story. Investigators traced the fatal 2022 crash in Norway.
Left engine
to a
failure
hard-clutch
detected.
engagement inside
Cross-shaft
the
torque
gearbox.
active.
A sudden, uncommanded lockup that transferred catastrophic torque through the drivetrain in a fraction of a second. At the precise moment the aircraft needed clean, controlled power to complete an emergency conversion. The redundancy engineered into the actuator, the flexibility engineered into the coupling. None of it changes the fact that the drivetrain, by design, has to work. There is no backup cross shaft. There is only the one. While the drivetrain problem was being solved on paper, the second one was waiting on the factory floor, and it traces directly back to the ghost of the 15-3. Whirling Flutter doesn't go away just because the rotor system works. It gets managed continuously through the choice of material in the rotor blades and hub themselves. Metal blades, spinning at prop rotor speed, subjected to constant cyclic loading as the blade sweeps through advancing and retreating positions relative to the aircraft's forward motion. Fatigue. Fatigue means microscopic cracks accumulating with every rotation, invisible until they aren't. A metal blade on a system already fighting whirling flutter is fighting two failure modes at once: structural fatigue and aeroelastic instability, with a material that has almost no capacity to absorb either one without transmitting the stress straight into the next component down the line. The V-22's rotor blades are built instead from carbon epoxy composite, laid up in specific fiber orientations to tune exactly how much the blade flexes under load and exactly how it damps vibration energy, rather than passing it downstream into the hub and the wing. But the blade isn't the only place engineers had to solve this. The rotor hub itself, the component connecting all three blades to the drive shaft, transmitting every ounce of lift and every cycle of vibration into the aircraft structure, uses something almost nobody outside the program has heard of: an S2 fiberglass yoke. A yoke, in this context, is the flexible structural spine the blades are mounted to, and building it from S2 fiberglass rather than metal means the entire hub assembly can flex slightly with every rotation, absorbing cyclic loads elastically instead of transmitting them as rigid, fatigue-accumulating stress. It's the same philosophy that shaped the actuator and the coupling, applied one more time, at the one point in the aircraft where whirling flutter, structural fatigue, and rotor dynamics all converge simultaneously. Damp the vibration at its source, and you don't need a heavier, stiffer, ultimately more fragile structure downstream to survive it. None of this comes free. Building composite structures at aerospace tolerance is not like machining metal. Carbon fiber is laid by hand, ply by ply, each layer oriented at a precise angle relative to the ones beneath it, because a composite's strength runs in the direction of its fibers and nowhere else. Get one ply's orientation wrong across a load-bearing section of blade or yoke, and you've built an invisible weak point into a component that's about to spend thousands of hours flexing at prop rotor RPM. Every finished part gets cured under heat and pressure in an autoclave, then scanned ultrasonically before it's cleared for the aircraft, because composite failure doesn't announce itself the way metal failure does. Metal bends, dents, gives visible warning before it breaks. A composite delamination can sit invisible between plies for years before it reveals itself catastrophically, under load, at altitude. This is the environment the entire program develops inside. Engineers solving one irreducible mechanical bet after another, each one an elegant answer to an impossible constraint, each one still, by definition, a single point of failure dressed up as redundancy. And for over a decade, it wasn't clear the program would survive long enough to matter. 2 prototypes went down in the space of 8 months in 2000. 19 Marines died near Marana, Arizona, when a rotor stalled asymmetrically on a steep, slow approach, a failure mode a single rotor helicopter physically cannot experience, because it requires 2 widely separated rotors losing lift independently rather than together. 4 more died in North Carolina months later, traced to a chafed hydraulic line and a related flight control fault. Congress opened investigations. News outlets started calling a widowmaker. cancellation was discussed openly on the floor of the House. The aircraft built to solve Desert One was, for a period of roughly 2 years, a bigger political liability than the helicopters it was supposed to replace. The redesign that followed touched almost every system this story has already walked through. Flight control software got the Vortex ring state envelope hard-coded directly into its logic, removing pilot judgment from the equation entirely in the specific descent conditions that caused a Marana crash. Hydraulic lines got rerouted and shielded against the chafing that caused the North Carolina crash. And by 2007, the redesigned aircraft deployed to Iraq, flying at roughly twice the cruising speed of a comparable helicopter, over roughly twice the range, while still able to land and take off from a spot no larger than a hovering helicopter needs. Exactly the mission profile Desert One proved was necessary in 1980 Aerodoctrine said was impossible. That's resolution. It isn't closure. Because the same drivetrain philosophy that made the aircraft possible in the first place. Accept one irreducible mechanical bed. Engineer every redundancy you can around it. And trust the math is still, decades later, the thing capable of bringing an Osprey down. The 2022 Norway crash and the fatal 2023 incident off the coast of Japan both trace back to failures inside that same drivetrain architecture. The gearbox, the clutch, the single shared torque path that makes the whole cross-shafting concept work in the first place. Every fix applied since 1981 has made that system safer. None of them have eliminated the fundamental trade the program made at the very beginning, that a single shaft, a single coupling, a single set of gearboxes would carry the entire weight of the aircraft's central safety promise. The V-22 exists today as the backbone of Marine Corps assault support, flown by the Air Force for special operations infiltration, by the Navy for carrier logistics, and its core capability, genuine vertical lift paired with fixed-wing range and speed, remains unmatched by anything else in production. Its drivetrain philosophy outlives its own controversies. The next generation of American Tiltrotors, aircraft like the Bell V-280 selected to replace the Army's Black Hawk fleet, inherit this architecture directly. The telescoping actuators, the flexible couplings, the composite yokes tuned to damp a vibration mode first identified when a prototype tore itself apart in the 1950s. Every one of those inherited components exists because engineers looked at an unsolvable contradiction, a rotor system that has to be two aerodynamically opposite things at once. And instead of eliminating the risk, they found ways to spread it, flex it, and damp it just enough to make the bet survivable most of the time. Most of the time is a phrase worth sitting with. 40 years after the JVX program began, the machine still runs on the same wager it started with. One shaft, one coupling, one gearbox, carrying a compromise that was never fully solved, only managed. If you want more stories like this, the real engineering decisions, the compromises that still fly, and the machines that shape the modern industrial world, subscribe to Factory Intelligence. New videos every week. Hit like if this one made you think differently about the machines we build. And drop a comment. What system should we break down next? This is Factory Intelligence. We'll see you in the next one.